And basically, this is going to be dealing with particles that we have seen, such as electrons. I mean, we have imagined, of course, all right, and but we know their effect. With, let's say, producing the current, producing voltage, all right, and waves. So, but where does the idea of waves come from? It basically comes from light, as we'll see in a second. So basically, the idea of waves came from the interference of light. Okay, if you have a source of light and you have two holes, such as the one you see at on the left, and what you see that the interference between these two light sources, okay, it gives an interference pattern which is up to the right, okay, and it's not like you are shooting some balls, okay. It's really like you have a wave and you have a wave pattern. This is the experiment. What you see is that you have a source of light, a double slit, and then you have an interference pattern. So this interference pattern is the main reason why we're sure now that light acts not only does not go in straight line, as it was done in geometrical optics. When you're dealing with the mirrors and lenses, but it really has a wavy nature. Okay, it really is a wave, and that's how we demonstrate it. It's a wave. Otherwise, there's no way to explain why. We do not explain why light is a simple particle traveling in a straight line. Okay, so the interference experiment has demonstrated a long time ago that the description of light is better done in terms of waves than in terms of just straight line. So this is the experiment that I'm referring to, that you have a beam of electrons or beam of particles, and you have a double slit, as you can see here. So if you assume that light is like particles, then we should have these two bright spots, okay? But what we have are these darks and bright spots, and of course, that this is resulted from the fact that light does not act as a particle, but is actually a wave. Later on, we're going to see that it also acts like a particle, and consequently, it has dual nature, a particle and wave. But to start with, is that first we're going to consider that light acts propagates not only in straight line, but also has a wave nature. This chapter will be divided into three main parts: black body radiation, photoelectric effect, and Bremsstrahlung radiation. Each one of these is going to give us an idea about the interaction between the nature of light, okay, and the interaction with the electrons, mainly with the electrons, okay. So each one of this will have one important message that we're gonna carry in order for us to have a much better understanding of nature and around us, and of light in particular. These three examples, they need what we're gonna call quantum mechanics. We are all familiar with classical mechanics or Newtonian mechanics. In the classical mechanics or Newtonian mechanics, particles are described as object with the center of mass, okay, and the quantities like the mass, the position, the velocity, the acceleration are defined, okay, and then considering the Newton's laws, we are able to understand their motion, their positions, their velocities, etc. In quantum mechanics, it's going to be quite different. The description is going to be quite different. Description, I repeat, okay, is going to be quite different. We can no longer talk about particles that are sitting at a given point with some velocity v. We must introduce something different, okay? So in order to have this description, several steps are needed, and historically that's what happened, okay? And now what we're going to do is see what are these major steps. So the first step is about black body radiation, okay? So as it's shown here, quantum mechanics is the study of relationship between energy, quanta, and matter. The most important point is that the effects of quantum mechanics are typically observed on the macroscopic scale, but become evident at the atomic and subatomic level. But of course, all what you guys see in with your eyes are described by quantum mechanics. Okay, so let's see the black body radiation issue and mainly the quantization of energy. Okay, now we have seen quantization in electricity and magnetism. We have seen when we're discussing electrons. And what I told you at the time was that any charge Q is formed of n times the elementary charge E, all right? So the quantization, it means that charge Q could not take any value, but it is an integer product of the elementary charge, okay? And now the quantization of energy is roughly the same idea, and that is the energy cannot take any value, but it has some discrete levels and discrete set of energy that it can take, okay? And this, of course, is going to lead us to understand why we have a continuum, such, for example, the rainbow, where it appears to be a continuum, okay, coming out of some of these individual emission lines, okay, or emission wavelength. So let's see what is the black body radiation. Very importantly, so you guys can see me because there's light coming, and now assume that I am, or you are, in a completely black room. There is no light coming inside it, and consequently, a priori, you should not be able to see me. However, what people found is that despite the fact that there is zero source of external light, bodies usually always emit their own light. They have their own emission, okay? This emission is called black body because it does not require any external light source to emit, okay? So this black body radiation is also called thermal radiation. We're going to see is going to be described by Stefan's law, and we're going to discuss the spectrum of radiation, which really depend on the temperature. Okay, so how to explain this black body radiation was mysterious for a long time. Okay, so what does the experimental data show us? It shows us that if I describe the intensity of light, this is the wavelength of light. Okay, then we have a maximum, and that this maximum depends on the temperature of the body. Okay, so the only thing which is happening here is really the body is emitting, has its temperature. Okay, so this, for example, is used in night viewing at night by these goggles. That guys, you must have seen this. Okay, and so what happened is that these atoms, inside these atoms, you have these electrons, and these electrons, they have their own energy. Okay, and this is what we call temperature. And so because of this temperature, these electrons are going around, okay, then they gain an energy and they lose energy. By losing energy, they emit light. So consequently, and this loss of energy is only done by simple collisions between the atoms. And this loss of light and this loss of energy is accompanied with a light emission. This light emission is called the black body radiation, okay? Now, of course, the more I have collisions, hence, the more the higher is my temperature, the more my intensity, as you can see here, the more the intensity is higher, but also the more the wavelength, the maximum of this light intensity shift towards smaller wavelength. Okay? So this is in a sense what is a black body radiation. Now, what Stefan's, what Wiens did in his experiment is that he noted what is the wavelength corresponding to the maximum intensity. Okay, and he changed the temperature of the body, and he noted the lambda max, which is the maximum of the lambda corresponding to the peak of the spectrum. Okay, and what he found is his law, and that is my lambda max is inversely proportional to the temperature, okay, in such a way that lambda max multiplied by the temperature is equal to this constant, 0.29 10 to the minus 2 meter multiplied by degrees Kelvin, okay, because lambda is in meter and the temperature here is in degrees Kelvin, okay. So what happened is that once again, as you increase the temperature, you have two things which are happening. One is the intensity of light increasing, okay, and the second is that this it shifts, the whole spectrum shifts towards smaller wavelength, okay. So the higher is my body, the smaller is my wavelength. Okay, but now we come to what we call the ultraviolet catastrophe. That if we try to describe these atoms in a classical nature, okay, using classical mechanical Newtonian mechanics, okay, then we were unable, scientists were unable to describe this effect. And what the main flaw was that this is the classical description, what you can see here, and the experimental data what you see in red, all right? And so the idea is that, okay, yes, scientists were able to describe the tail of the light intensity of the spectrum, but they were unable to describe how the intensity goes back down to zero when the wavelength goes to zero. Okay, and so this is what is referred in literature to the catastrophe theory, and this is one of the indicators, because this has been observed long time ago. This is one of the strong indicators that classical mechanics is unable to describe a physical phenomenon. And this was actually quite new at the time, okay? Because let's say in the early 19th century, people thought that classical mechanics, that everything they were able to describe everything, okay? And this was one of these examples that the classical mechanics failed. So how to still solve this issue? Well, this was solved by a guy named Max Planck. Okay, he solved it by considering that the energy does not take a continuum. It's not a continuum, but it's discrete. Okay, to give you, just make sure that we understand what the continuum means and what discrete means. A continuum means, let's say, it means that you have a light at all intensities, okay? At all wavelengths, excuse me, at all wavelengths. Discrete, it means that you have light only at discrete wavelength and not at all wavelengths, all right? So if we adapt this, this theory, okay, and that is light is quantized, okay, and not a continuum, and a light will act as a resonator and not just simple, it has a continuum frequency, then people were able to solve this problem and were able to describe So what is Planck's quantization of energy? The energy is radiated and absorbed, okay, in quantities that is divisible by discrete energy elements, which is called En, such that each of these energy elements is proportional to the frequency with which each individual radiated energy. So basically, if I have a source of light, okay, at a given frequency, then the atom is able to absorb this frequency, okay, which is equal to NHF, where N is called the quantum number. Now, of course, if N is equal to 1, then we have E is equal to HF. So if we adapt that the interaction of the emission of light is not happening in a continuous fashion, but rather in a discrete fashion, okay, in this case, we are able to solve the ultraviolet catastrophe and thus to understand how black body radiation occur. So this vibration occur at the frequency F, okay? Of course, I can replace F by C over lambda, okay, by C over lambda, and in this case, I'm going to obtain the energy, En is equal to NHC over lambda, okay, where I remind you, lambda is the wavelength, F is the frequency of the vibration, okay. Now, associated to that, we will come back to this equation here. The momentum P is equal to H over lambda, is equal to P equal to H over lambda. So this was the first, this is our friend Mr. Max Planck, and he was awarded the Nobel Prize in 1918 for discovering the quantized nature of energy. Okay, so what do we in summary, what do we have? One is that bodies emit light even in the absence of external source. Okay, this emission of light take the form of the spectrum increases, reaches maximum, and then decreases. This spectrum depends only on the temperature. Okay, the maximum. So if the temperature is higher, the intensity is higher. And if the temperature is higher, lambda is smaller. The lambda max is smaller. The law at which lambda max depend on temperature is called Green's law, and is described by lambda max multiplied by temperature is equal to 0.29 10 to the minus 2 meter Kelvin. In order to explain this black body radiation, we need to consider the energy not as a continuum, but as discrete. Okay. And it occurs according to the formula E is equal to NHF. H is called the Planck's constant. F is the frequency of the vibration, and N is called the quantum number. Okay, if this is done, then this ultraviolet catastrophe is no longer takes place, because we are now using quantum mechanics and not classical mechanics, and we are able to understand black body radiation. So this is the first part of this lecture. Do you have questions so far? If yes, please just unmute, and then let's please ask your questions before we move on to the second part. Okay, if no questions, let me continue. So now what we know is that electrons, okay, just by simple collisions, okay, they emit light. So there's a relationship between the atom and light. Okay, of course, but this is something which, when the photoelectric effect, the ultraviolet catastrophe, the black body radiation, what really shown is that electrons, what they do is that they emit light on their own. There is no need for external source. Okay, so electrons emit light. Now, in the photoelectric effect, we're going to see that light can act like particles. So remember, we start with geometric optics. It was there since the Greek. Okay, they studied geometric optics. They have lenses, mirrors, etc. Okay, so people thought that light moved in straight lines. Then we have the interference experiment. The interference experiment showed us that light, yes, it moved in a straight line, but it is a wave. Okay. Now what we're going to see, that light is not only moving a straight line as a wave, but also acts like a particle. Okay, so it can punch. Okay, it can induce momentum, and of course it can induce energy, acting exactly like a particle, basically like an electron, for example. So let's see, what is this photoelectric effect. So when light is incident on certain metallic surfaces, electrons are emitted from the surface. Okay, this is called the photoelectric effect. The emitted electrons are called photoelectrons, and the resultant current is called the photocurrent, just to make sure that we each other. Experimentally, this effect was detected by our friend Mr. Hertz, that we have discussed his major discovery that electromagnetic waves are actually described by the same laws of physics as electricity and magnetism. Okay, the successful explanation was given later on by Albert Einstein, who received the Nobel Prize for his paper. Of course, the discovery of Albert Einstein, in the same way the discovery of Max Planck, they refer not only to explaining this photoelectric effect, but using this photoelectric effect, which is an experimental result, to have a much better understanding of the nature around us. Okay? So let us describe what this photoelectric effect is. So consider that I have a tube from which I removed all matter. So it's a vacuum. So I remove all particles from this tube. Okay? And then I'm going to have two electrodes, okay, the E electron and the C electron. Okay? Between them, I'm going to apply a voltage, V. Okay? And in order to see whether I'm able to generate a current, I'm going to put an ammeter A. Okay? I've got a voltmeter if you want and a power supply. All right? And the C has the property of having a simple hole in it. Okay? From this hole, I can shine light, okay, which is going to hit E, okay? And the idea is that when the light arrives at E, then I'm going to record a current. Remember the definition of a current. The current is basically circulating particles, okay? So when I record a current, what does that mean? It means that the electron, even though there's no connection, there's no wire between E and C, okay? But yet, electrons are flying from E towards C, going into the battery and coming back to E. And so this is basically the electron motion. Consequently, I'm going to have a current in the opposite direction, which is going to occur, and that's the critical point, only when I have light. So if I have the same process at the same potential difference and I turn off my light, I don't have a current. Turn on the light, I have a current. Okay? So this is what we call the photoelectric effect. From the name, you can clearly see that it has two components. It has the photo, which is the photon, and we'll see in just a second, which is light, and electric, which is basically the electricity, the current that you know, the battery, the potential difference that you guys all know, I hope, by now, okay? So, what are the observations? The observation is that, okay, you know what, I have a battery, I can change the voltage of the battery, okay? And I can have what we call, I can have the voltage on the x-axis, okay? And the current on the y-axis, that's called the IV trace. So, the photoelectric current voltage graph, it looks like this. If my voltage is negative, okay, it starts to be quite negative, I have no current whatsoever, very negative. Until it hit a potential delta Vs, that we call the stopping potential, okay. After this potential, then I start to record the current, okay. But once again, all this with the light on. Okay, once again, if you stop the light, there's no current. So I have my light on, okay, and I'm changing my battery, all right? And changing my battery, I'm gonna stop now for a second, and then we continue. Let's continue. Okay. Okay, so light on again, and I'm changing my battery, all right? And I'm increasing my potential difference going, let's say, from minus 50 volt to plus 50 volt, okay? So as I am increasing my voltage or decreasing my voltage to absolute values, what I notice is that there's a stopping, what we call the stopping potential, okay? And this stopping potential is defined as the potential difference, okay, from which, starting which, I start to have a current, I. So in this, we will see in a second why the maximum kinetic energy is equal to this potential difference multiplied by delta Vs. Remember, minus E delta Vs is the potential energy, right? I hope that you remember that. Delta V is the potential difference. When you multiply it by Q, this gives you a potential difference, a potential energy difference. Okay. Here, what we are saying is that at this potential, all the potential energy is transformed into kinetic energy of the electrons. Okay, and such that the total kinetic energy is equal to the total potential energy. Okay, since at rest, since electrons were assumed to be at rest without the application of the potential difference, then Ke max is equal to minus E delta Vs. Okay, so what are the observations? No electrons are emitted if the incident light frequency is below some cutoff. So now, if I change the light frequency, not only the potential difference, I also have a dependence on the amount of current that I am recording. Okay, so this is also, we're going to have a frequency cutoff, okay, or cutoff frequency that is characteristic of the material eliminated. So basically, if I change the material here, if I change C and E, okay, this cutoff frequency changes. Okay. Second point, the maximum kinetic energy of the electron, of the photoelectrons, is independent of the light intensity. And here you need to just make sure that we understand each other. When we talk about light intensity, okay, usually in physics, we talk about fixed frequency and much more photons. That is light intensity. So when we say here is independent of the light intensity, this means that I fix my frequency and then I change my light intensity. Let's do another example. If you take, let's say, a laser pointer, okay? A laser pointer emits photons, red photons, okay? Red light. So the idea here is that you fix this red light, but you change the amount of red light you're emitting. If you do so, then one can verify that the maximum kinetic energy of the photoelectrons is independent of the light intensity. However, the maximum kinetic energy of the photoelectrons increases with the increasing light frequency. Okay, so if I increase my frequency, then the maximum increases. So, and the final point is that electrons are emitted from the surface almost instantaneously, even at low intensities. Basically, as soon as I put my light, I have my current low. That's what it means. It's instant. It is instantaneous. Okay. So now, how are we going to observe? How are we going to understand or to explain the role of light? But since it is a light, it's a wave. It's going to hit the metal, and then that's it. Okay. In order to explain this photoelectric effect, what Einstein did is that he imagined that this is a straight line, this is a wave, but now imagine that I'm going to have a small particle light which is doing this wave. It's not just, just a wave. It's a particle. This particle, we're going to call it a photon. And it's going to have an energy which actually now goes back to our friend Mr. Planck, which is equal to HF. Okay? The important point is that these photons will now act not only as a wave, but also as particles. And so now these particles, they hit an electron, okay? Each particle wave of photon has HF. So the higher is F, the more I have energy of the photon. And consequently, the Ke max will increase, okay? Because I'm hitting it at a higher energy, okay? And so what Einstein did, he extended Planck's idea of quantization of electromagnetic radiation and the idea that light might act as a particle and not only as a wave. And this is huge, of course. because now the whole idea, our ideas of light has completely changed from single line to a wave and to a particle going with a wave. Okay, so if we consider it like this once again, so we have this particle going like that and hitting another electron, light coming like this, hitting an electron. This electron gained this energy. It kicked out of the material, okay? But it kicked out only if it has enough energy to overcome what we're going to call the work function, okay? So what is the work function? The work function is the energy of that the electrons have to remain inside the atom or inside the metal, okay? So clearly, this photon energy must overcome what we're going to call the work function, such that this electron will have a kinetic energy. So now, look what happened. If first, according to this formula, Ke max equal to HF minus phi, F must be greater than some value, which is equal to phi. Otherwise, this value, HF minus phi, is negative, and I don't have a kinetic energy. Okay? This is the cutoff frequency that we have seen here, cutoff frequency. So the cutoff frequency, okay, comes from the fact that HF minus phi must be greater than 0. Okay? At equal to 0, HF equal to phi, which is the work function again, okay, then I have just the necessary amount of energy from the photon to kick the electron out, but it doesn't have a kinetic energy yet. Okay, so this explains why I have a cutoff frequency. Now, in this equation here, Ke max of the electron equal to HF minus phi, you can clearly see, I hope, that there is no dependence on the number of electrons. Okay, I can have 1 electron, I can have 10 electrons, I can have 1 million electrons. What the maximum kinetic energy does not depend on the number. Of course, the number of electrons that are contributing to the current will depend on the number of photons, but not the kinetic energy. And there's a distinction between the two. The kinetic energy is 1/2 mv squared. Okay, so that's the energy, the velocity of the electrons. Okay, so this velocity does not depend on the number of photons. So if you have 1 photon hitting or 100 photons hitting, is the same kinetic energy, and this kinetic energy is dictated by the amount of the amount of energy that the electron is giving to the electrons minus the amount of energy that the metal is applying to make it remain in the metal. Okay, I repeat. So the number of photons, consequently, the intensity of light does not affect the kinetic energy. But of course, if you go back here, the light, the intensity that you see the current. The y-axis here is the current. The amount of current, of course, it depends on the amount of light intensity that you put. Okay, but not the kinetic energy. So please be careful about this differentiation between the kinetic energy, which is equal to 1/2 mv squared, and the current, which is equal to n delta q over delta t, if you recall, which is really depend on the light intensity. So the more I have photons, the more I have electrons. But the more I have photons, I don't have more kinetic energy. I have the same kinetic energy, which is dictated by this equation. So if I plot now the kinetic energy maximum with respect